Video number 33, Newton's Incredible Luck. This is my first video directly in English, since its objective is slightly different from the previous ones, and I believe that most persons interested by its contents are accustomed, at least, to scientific English. Here we are interested in understanding why Newton's theory of gravitation is so efficient. Newton derived his formula for the gravitational field produced by a point-like massive body, which was quite realistic since the distances between planets and stars are very large compared to their diameters. But in fact, the situation is even better, and in this sense, Newton was fortunate. Calculations concerning planets and stars are indeed much more precise than what would follow by a vague point-like approximation. Since it turns out that when the object is spherically symmetric with respect to mass distribution, it behaves exactly as if all the mass were located at the center. This allows very precise astronomical calculations, even when the distances are not very large compared to diameters, since planets and stars are close to spherically symmetric. This result is classically proved for the gravitational field by applying the Gauss theorem on the total flux through a closed surface enclosing the massive body and exploiting the rotational invariance. But since the result on spherical bodies is so important in astrophysics, I shall now give a direct proof relying only on the mathematical tools familiar to all undergraduate students in mathematics or physics. First, let us recall the law for point masses. It simply states that the gravitational force between two point-like bodies is proportional to the product of their masses and inversely proportional to the square of the distance. When the massive bodies have a non-negligible spatial extension, one might imagine that the force emanates from the center of masses. But the simple example of two equal point masses shows that it is not true in general. For instance, for a point close to one of the masses, the resulting gravitational field is much stronger than what it would be if the two masses were transferred to the middle. In order to formulate properly the result, we consider a positive number capital R and the ball BR centered at the origin with radius R. We consider a non-negative spherically symmetric density function mu, and we denote by capital M the total mass of the spherical body. Given a point U exterior to the ball BR, we claim that the integral over BR of mu of norm of x divided by the norm of u minus x is equal to capital M divided by the norm of u, and the integral over BR of mu of norm of x multiplied by the vector u minus x and divided by the norm of u minus x to the cube is equal to capital M vector u divided by the norm of u to the cube. It is in fact sufficient to prove the first formula concerning the potential, since it implies the second by taking the gradients. We denote by capital U the norm of the vector u, and using spherical coordinates x equal r cosine theta, r sine theta cosine phi, r sine theta sine phi, we see that the integral to be computed is the integral from 0 to r of mu of r, integral from 0 to 2 pi, of the integral from 0 to pi of r squared sine theta divided by the norm of u minus x d theta d phi dr. Since the integral is invariant by all rotations around the origin, it is sufficient to consider the case where small u is equal to capital U, comma 0, comma 0, in which case the integral becomes, by integrating with respect to phi first, integral from 0 to r of 2 pi r squared mu of r j of r dr, with j of r equal the integral from 0 to pi of sine theta divided by the norm of u minus x d theta equal the integral from 0 to pi of sine theta divided by the square root of u squared plus r squared minus 2u cosine theta d theta. We claim that for all r in 0 capital R, j of r is equal to 2 over capital U. Indeed, the change of variable cosine theta equal v gives g of r equals the integral from minus 1 to 1 of dv divided by the square root of u squared plus r squared minus 2urv. Now, we have that the derivative with respect to v of the square root of u squared plus r squared minus 2urv is equal to minus ur divided by the square root of u squared plus r squared minus 2urv. After a simple computation that you can see on the screen, it turns out that j of r equals 2 over capital U. Then it turns out that the integral to be computed, the opposite of the gravitational potential, equals 1 over capital U times the integral from 0 to r of 4 pi r squared mu of r dr equal capital M divided by U. Remark: we actually proved the geometric identity. Whenever the norm of U is greater than R, which is positive, the integral over SR of d sigma divided by the norm of U minus x is equal to the surface of SR divided by the norm of U equal 4 pi r squared divided by the norm of U, with SR, the sphere of radius r centered at 0, and d sigma, the area element of the sphere. Conclusion: Newton's gravitational law is very efficient because it has a strong geometric background, and historically, the comparison with propagation of light played a basic role to formulate it with the help of Robert Hooke. Newton was also very interested in optics, so that, in a sense, all of this is not the result of chance. The confirmation that the 1 over r potential implies the 3 Kepler's laws was the icing on the cake.